I'm presenting my project, which shows that even when no researchers nor readers are biased, we could still have publication bias. We rely on scientific evidence for making important decisions. Imagine you're a doctor deciding whether to prescribe a new medication. You look up online, there are 10 studies, and there are 7 positive results, 3 negative results, and you decide for yourself that's probably good enough. And later, you read this New York Times article, which says, and I quote, that pharmaceutical companies never published about a third of the drug trials that they conducted to win the government approval, misleading the doctors and consumers regarding the true effectiveness. Concretely, while 94% of the positive results were published, only 14% of the negative results, non-positive results were published. And moreover, even among the negative results that were published, there were 14 of them, 11 of them sort of conveyed the positive outcome. So they kind of sort of specification searches and so on. Given this severity of selective reporting, the publication bias, which is that the literature is not representative of the underlying subject that it studies, there are heated controversy on how to implement academic publication, such as pre-analysis plan, the level of p-values, and maybe stars in the regression tables. So what I show in this paper is, in fact, that maybe when there are information aggregation frictions, there could still be publication bias, even when the researchers themselves are purely social welfare maximizing and unbiased. And moreover, that the reporting practice with publication bias could be not so bad. Okay. Well, how could that be? If the researchers have no conflict of interest with the reader, why would they not report all the results as they know? The key to my approach is that readers might not take into account all the details of the paper to make their decision. In particular, they might just compare the number of positive results versus negative results to decide what to do. So surely, if you have all the time and statistical knowledge and memory, then you would look at the coefficient and standard errors and all the caveats of the paper to make your decision. But if you don't, this is kind of the common and simplest alternative. Well, you might say, maybe people are more sophisticated, but there's even a very high-profile case that went to President Obama in 2013 that said that 97% of climate papers stating a position on human-caused global warming agree that global warming is happening. And this summary was a summary of 12,000 scientific published papers. So they never actually looked into the details of the paper, but rather just referred to the abstract. And there are evidence that even experts in statistics have this dichotomized kind of thinking. And what I show in this paper is, in fact, that publication bias could be seen as counterbalancing this inefficient dichotomous thinking. The researchers independently conduct their experiments and learn and obtain their treatment effect estimates, beta I, that has a standard error sigma I. So you can think of this beta I to be the sum of true treatment effect plus the noise. And they report their results of either to recommend a policy yes, or recommend not to implement the policy no, or not to report that study. Think of these researchers not as independent authors in the real world, but as a collection of referees, editors, and authors who jointly decide what to report. So there's no referee process in this thought experiment. And then there's a policymaker who read how many positive results there are, negative results there are, and decide whether to implement the policy, so do or not do not. And that's, for example, adopting medication or not. It's a simplifying assumption that there are only 2 researchers. I could actually extend that to n researchers. It's also a simplifying assumption that this n number of researchers is known, but this could be extended to the case where... Thank you. So yes, you could extend to the case where number of researchers is unknown, and you could also extend this to the case where the researchers report sequentially rather than simultaneously. All researchers and policymakers are social welfare maximizing, and social welfare is the benefit minus the cost of the policy when they implement the policy, and normalized to 0 when they do not implement the policy. The distribution of the benefit of the policy and the cost of policy is known to everybody. My main result focuses on the case in which the standard error is the same across everyone, to simplify, and normalize to the case in which the cost of policy is 0. In the socially optimal and locally stable, which means it's an empirically plausible Nash equilibrium, the set of behavioral rules in which everybody is doing their best given everybody else's behavior rules, that the Nash equilibrium is going to have the policymaker who implement the policy if and only if there were strictly more positive results than the negative results. And the researchers would adopt a cutoff strategy in which they would recommend the policy if their estimate is high enough. They would recommend not to implement the policy if the estimate is low enough. And in between, there's a positive probability of not reporting. And it turns out that these thresholds are asymmetric. And in particular, the researchers have to be more confident to recommend not to implement the policy than to recommend the policy, so that when meta-analysts go into the estimate and take its average, it turns out that the reported studies have upward bias of the estimates that underlie them. So let me explain the reason behind the optimality and asymmetry of this omission. So the researchers know a lot more than what they are allowed to say. Right? They know the strengths of their information rather than only the sign. So in a way, allowing for a possibility of omission is enriching a message space, so they're allowed to convey more information, so that would make the decision better. And and the asymmetry arises because of the pivotality condition. So let me explain that. So when deciding whether to recommend the policy or not to recommend the policy, so not reporting the results, this decision is consequential only when another researcher did not report his study. So because that would turn from 0, 0 to 1, 0. In contrast, when deciding to recommend not to implement the policy, so that's beta lower bar, that decision is consequential only when another researcher reported positive results. So that would change from 1, 0 to 1, 1. And because of this asymmetry in when certain reports are consequential, this kind of bias arises. Okay, let me explain that again. So deciding to recommend the policy is consequential only when another researcher received an intermediate estimate, because that would turn from 0, 0 to 1, 0. And in contrast, recommending not to implement the policy is consequential only when another person found a very high estimate, so that it would turn from 1, 0 to 1, 1. And because you would try to consider, the rational researcher would try to consider what another researcher must have observed, at the time when the reports are consequential, this asymmetry arises. So my second result is actually not only about omission, but about inflation. And in particular, it turned out that the socially optimal thresholds of reporting positive results or omitting is going to be inconsistent with the p-value approach or the sort of constant t-static rule. And consider the case in which the standard error has now some known distribution and the cost of policy is bigger than 0. So I'm going to use this plot where x-axis is a standard error of each study and y-axis is a coefficient beta I of each study. So each information that the researcher has can be represented by a position on this plane. So the beta upper bar, which is a threshold to recommend the policy or omitting the study, is going to be given by this line, and beta under bar is going to be given by this line. And so what this shows is that, let's say, given a particular value of standard error, if you have sufficiently high coefficient, you would recommend the policy. If it is not so high, you would not report it. If it is sufficiently low, you would recommend not to implement the policy. So what this shows is that if there's like a rule of thumb publication rule that imposes a particular constant p-value or t-statistic that requires some linear approximation of this line, there is going to be a discrepancy between the optimal reporting threshold and the t-statistic rule. And in particular, it might not be very large, but there might be a small region in which the t-statistics rule is going to say it's not significant, but it might be very reasonable to, in fact, recommend the policy by announcing positive results. I think that this is this particular prediction is reasonable because when you have very, very noisy study, then even when certain results are marginally significant, you might not still recommend it. Or when you have very precise studies where, let's say you have administrative data and find a marginally significant result, well, the coefficient is not very large, so you would still not say announce positive results. And so I think sort of the model is getting at something that actually speaks to the real world decision. And there's a statistical reason why the t-statistic approach and this Bayesian learning models are not compatible with each other. And that is that the t-statistics divides the coefficient by standard error because it's a normalization for the convergence that occurs at the root n, at the rate root n, whereas the Bayes rule is going to be a weighted sum of each coefficient where the weights is inversely proportional to the variance, which is proportional to the sample size. And so there's a general nonlinearity in the Bayesian decision making that cannot be captured by a constant t-statistic. So this model has a prediction on how the meta-analysis data set might look like. So I again plot standard error on the x-axis and coefficient on the y-axis. This is a simulated data. So if the true effect of the estimate is constant across the accurate as a precision of the study, then the estimates are going to fan out because noisier studies have sort of higher dispersion, more dispersion in the point estimates. What the model predicts, and this is very qualitative, and is that the omission of the study occurs only among the noisy studies that have not so extreme coefficients. What this means is that when the null results or negative results are published, they are either very precisely estimated null results. So think of RCT with 2,000 patients that show that the drug that people used to believe were effective is not effective. Or maybe not so precise RCTs, like RCT with 50 patients that shows that the drug actually harms people or something like that. These tend to be publishable. And this kind of pattern of publication selection is very important for bias correction in meta-analysis because it guides how we want to impute the missing studies. And it turned out that this model this prediction is different than other commonly used models of publication selection. In the paper, I refer to 3 of them. Here, I'm going to focus on one that's commonly used in economics, including Garrett. This is a uniform omission model by Larry Hedges in 1992, which suggests that the study is uniformly less likely to be published if it is statistically insignificant. What this says is that the precision of the study is not going to affect the probability of publication conditional on being a null result. So the story is that people are just chasing for stars and so on. So I compare an observed and predicted distribution of null results to see what the pattern looks like. And in particular, I take the data by Dolgolievas and Radoku in 2003 that meta-analyzes the effect of labor unions on firm productivity and focused on 54 stat estimates whose papers have their binary conclusion in their abstract introduction or conclusion, so it is sort of meant for vote counting. This is the actual data of the significant results. And using the sort of commonly used assumption of the uniform omission model, like normality of the distribution, orthogonality with the error term, and that assuming no selection of the significant results, I could impute by using sort of the best guess of these estimates what the underlying distribution of the null results must have looked like to observe these actual significant results. Now I can now I'm going to plot the actual observed null results, and it looks like this. So as you can see, among precisely estimated results, there are omission, but less of it. And among the noisier studies, there are far fewer observed study estimates reported compared to what is predicted. Specifically, whereas only 30% of the null results are predicted to have standard error less than 0.1, as much as 40% of the observed null results have standard error less than 0.1. And this difference of 40% is a Kolmogorov-Smirnov test that I formalized in the paper. And the probability of observing this discrepancy under the null that these two distributions are equal is, in this direction, is only 0.15%. And so this is not what the uniform omission model predicts, but this regularity is what my model explains. So let me end with 2 caveats. I'm not saying that each researcher is actually social welfare maximizing in the pure sense. Remember that the researcher in the model is like a collection of authors and referees and editors. But what I think it provides is a formal and rational model of what we mean by interesting results. People are just looking for interesting results, and they are the results that are conclusive enough so that the simple conclusions are easily interpretable. I'm certainly not saying that any kind of publication bias is acceptable. Of course, not outright sort of publication of data. Or in the case when there are clearly very significant biased incentives, like in medical research where pharmaceutical companies themselves implement the trials, or when meta-analyses are common, maybe my analysis is not very relevant. But for the observational studies in economics where I don't think people have a very, very biased motive, or the meta-analysis is difficult because people use different methodologies, then I think this sort of model speaks to how we think about the publication bias. So my overall message that I want to convey is that publication bias is a very sensitive issue, and people sometimes do not correct for publication bias in meta-analysis, thinking that it's kind of a criticism to the literature. Well, maybe it needs not be, and hopefully this understanding could allow us to think about publication bias in a more positive and straightforward mindset. So, thank you.
About whether this is how the world works or not, and I think we can think of cases where people in absorbing and interpreting evidence have very simple decision rules, but we also have professional societies, National Academy reports, all these groups of experts that are meant to aggregate the evidence in a sophisticated way and deliver a sort of more nuanced message. So I guess maybe we live in a mixed world, but I just wanted to get your sense of clearly the assumption of the vote counting sort of makes everything else possible and sort of sets up what you find, and I just want you to get your sense about where this is the right model and where it may not be the right model in real world decision making.
So, oops. Okay. So let me. No, I think I have it. Yeah. Thank you. So even when reviewers take time to summarize results, I do think that when methodological differences are large, they tend to summarize results in tables and so on without fully sophisticated statistical methods, and so they have more impressionist approach to aggregating different estimates. So here I think that the vote counting could actually be a reasonably relevant way of thinking about it, although of course it might not be dichotomous exactly and they're intermediate and so on. And so I do think that when they are regular practice of meta-analysis, and I think that the right approach is that that would hopefully make this model less relevant, and that would push us to allow for a more full reporting. Another important assumption is actually this rationality and conditioning on what other people do. And I think of this result really as heuristic that drive people's decision rather than people thinking literally in this way. And yes, so that's my interpretation.